Okay. Good evening, everyone. Welcome back to your ninth discussion session in Mechanical Behaviour of Materials. I am Pragyandipta Mishra, a research scholar from Department of Applied Mechanics and Biomedical Engineering at IIT Madras. Today, we'll be discussing about strengthening mechanisms. Essentially, how do you strengthen an alloy? What goes into this strengthening process? And what is essentially the principle behind this strengthening? Then the various methods by which we can do this strengthening, and we'll be going in detail about a couple of those strengthening mechanisms today and following it up in the upcoming week as well. Okay, so let's begin with the first and foremost thing. What exactly do we mean by strengthening mechanism? Essentially, what do we mean by this strengthening mechanism? Why do we need to talk about this strengthening mechanism in the first place? So, any alloy system, any metal or pure metal for that matter, anything that is made out of metal, any system, essentially needs certain properties or needs certain things that allow us to use it as a structural material, right? We have discussed this before. So if you need to use a material for as structural material, there are certain criteria that the material has to fulfill. So one of the most important criteria is strength, right? Now, inherently the material might have some value of strength, as we have figured out using like modulus of elasticity and other things, parameters, that there are some certain factors which are associated with strength, right? But there are other ways to improve the strength of the material, right? So there are mechanisms in place which can help us improve the strengthening mechanism, strengthening behavior of any material, right? So when we talk about strengthening mechanisms, what we are essentially telling is we are trying to increase the strength of any material system, any alloy system. And how could we achieve that? So essentially the first thing that we are trying to do is we are trying to increase the strength. And how do we achieve that? By restricting the movement of dislocation. Now, why do I say that restricting the movement of dislocations help us in strengthening a material? Essentially, what are dislocations doing? Till now, like last few weeks when we talked about dislocations, what did we see? What is exactly dislocation doing? It is essentially causing a plastic flow or yielding happening within the material, right? So if dislocation moves, we'll see that the plastic flow will start, yielding will start, right? Now, what can we do? If we are restricting the motion of this dislocation, what essentially are we doing? Essentially, what we are trying to do is we are trying to ensure that now this dislocation motion does not happen very freely. So, in effect, yielding will not also happen very freely, right? Flow of metal will not happen very freely. Therefore, the failure will not happen very fast, and the strength would improve, right? So that is the essential process by which we are strengthening any material system, right? So any method that we study from here on for strengthening is essentially involving restricting the movement of dislocation. Okay, so because this is like the most direct way of improving the strength, you can always do something to the material system so that the movement of dislocation is retarded. Now, when that happens, the material gets strengthened automatically. Okay, so let's talk about what are the different methods by which this strengthening can be done. Okay, now this will depend on what and all dislocations can essentially interact with. Okay, so if you want to talk about methods of strengthening, so if you want to talk about methods of strengthening, you have to essentially look at what and all do dislocations interact with, and if we can influence those particular things in some way or the other so that dislocation motion gets retarded, right? That would be the simplest way to go about it. So let's see what and all can dislocation interact with. First and foremost, of course, goes without saying, it can interact with other dislocations, right? Dislocations basically can interact with each other and they can influence the motion of other dislocations. We have studied about this in the previous class, right? About how dislocation interactions or dislocation influence each other's motion. Next is grain boundary. Again, we have talked about how there are grain boundaries between within the material system, which are formed when different orientations of grains are formed at the simultaneously, so that there'll be a boundary between two grains which are at different orientation. Now that this grain boundary can also act as source or sink for dislocation. So when that happens, this dislocation motion actually is like kind of stopped, restricted, or sometimes sometimes even like the dislocation motion is completely stopped because of this grain boundary. So this grain boundary can also influence the dislocation motion. Third thing is solute atoms. So presence of other atoms in the system, right? Like for instance, if you have a metal matrix of iron, if you have other atoms like chromium, manganese, etc. added to the system, they can also influence the dislocation motion. So dislocation will interact with these solute atoms, and essentially the motion will get changed according to how these interactions are. Okay. Next are precipitates. Okay. Now precipitates are another important materials, like another important, for lack of a better word, I would say it's like another phase which is present within the material system that can influence the property of the entire material system. So essentially precipitates are formed when you are dissolving a higher quantity of any solute atom in a particular metal matrix. Okay, so supposedly, like if you are adding chromium to iron, okay, so there is a certain threshold up to which chromium can be dissolved within iron. Okay, now this is an example. Okay, like you might not form precipitate this way for chromium and iron, but I'm just giving you a random example. Okay, or let me give you a more specific example where that is actually possible. Okay, let's say I take magnesium as my matrix, Mg as my matrix, and I'm adding aluminium to it. Okay, and I keep adding aluminium to it. Now there is a threshold up to which aluminium can be dissolved within the magnesium matrix. Okay. Beyond that, what happens is now aluminium has is present in more quantity. If you keep on adding aluminium, it will be present in more and more quantities. Now, because of this presence of this extra quantity of aluminium, they start coming out as a separate phase. Okay, so now this aluminium can also mix with the matrix element, that is magnesium, and they can together form some extra particles which might come out as a separate phase. Okay, so that the limit of aluminium within the matrix remains within the threshold. Okay, so this extra phase comes out as a separate particle, and that is something known as precipitate. Okay, now these precipitates are very, very important in material behavior studies, mainly because these precipitates actually help us in influencing the behavior in a lot of different ways. Okay, and one of the best ways is, of course, by restricting the motion of dislocation. Okay, so this precipitate is essentially like you can think of it like as extra phases or particles which are present within the material structure, which helps in influencing the behavior of the material. Okay, overall material behavior. Okay, and next is dispersoids. So dispersoids are another type of particles which are added. We'll come back to what dispersoids are towards the end of today's lectures, but you can understand it in this way that dispersoids are essentially something that do not mix with the matrix but are present as an extra inclusion or phase within the structure. Okay. Now they differ from solute atoms and precipitate in this way. Now solute atoms are something that get dissolved within the solution. So essentially you are adding the material, some particular element within another element. Now that get dissolved within some threshold limit. So that will form solute atoms. Okay. Now if you go beyond the threshold limit, that will form precipitates. Okay. And dispersoids are something that does not get dissolved. So this is completely separate from solute atoms or precipitate because they do not get dissolved. They are present as separate phase from the beginning itself, and they also influence the dislocation motion. So therefore, dislocations interact with them, and to an extent, the dislocation motion gets influenced. Okay. So depending on how these interactions happen or which interactions happen, we can name particular types of strengthening mechanism that happens due to this. Okay. So if dislocation interacts with other dislocation, we can say that the type of strengthening mechanism that happens is known as strain hardening. Is also known as work hardening. Okay. Now they interact with grain boundary. So then we just directly call it grain boundary strengthening. No specific extra term there. Okay. Now when they interact with solute atoms, we call it solid solution strengthening. Okay. So essentially by the name you can guess that you're adding solid to a solution and causing some strengthening mechanism. Okay. So that is known as solid solution strengthening. Okay. Now, if you're adding precipitates or interactions with precipitates, if you're looking at that and how that influences dislocation motion, then we'll call it precipitate strengthening. And finally, dispersoid. So we just call it dispersion strengthening. Okay. Okay. So let's study about all these methods one by one in detail, starting with precipitation strengthening. Okay. Now, precipitation strengthening is also known as age hardening. Okay, there's another term that is used to refer to precipitate strengthening. So, if you come across age hardening anywhere, just know that it's same as precipitate strengthening. Don't get confused. Okay. Essentially, you will understand why we call it age, like why we use the word age to denote precipitate strengthening. Like once we go through the theory part. So that age actually refers to something within this precipitate strengthening mechanism. And hardening, of course, is like strengthening. So that's how we call it. So like I said, precipitates are like extra phases, like they're separate phases, which are which are derived from the matrix when you add extra amount of elements within the microstructure. Okay, so when you're adding more and more amount of elements above and beyond the limit up to which like this precipitate can the particular matrix can dissolve, then the precipitates will essentially come out. Okay, so one important thing to note about precipitates is the precipitates are very fine. So they're very small particles. Okay, they're very fine particles, and they restrict the motion of dislocation. Thus increasing the strength. Okay, essentially precipitate strengthening will involve these very fine particles, like not allowing the dislocation motion to be like free, and therefore the strength would increase. Okay, so that is the basic premise of precipitate strengthening. So how do we obtain this precipitate? So like I talked about, like these precipitates are formed due to oversaturation or something like that. Let's see exactly how do we form this precipitate. So what is the basic criteria? What is the basic criteria to obtain precipitates? So let's plot uh, a temperature versus weight curve for like any specific alloy system. Let's say like we are talking about aluminum copper alloy. Okay, let's see how this looks like. So this is temperature. Okay, and then this is weight percentage of element B. Okay, so essentially initially what we will have is some portion of the curve where there will be only alpha phase. Okay, let me just finish drawing the whole thing first. Okay, so this line that I marked in red, this is known as solver's line. So essentially solver's line is like a minimum criteria. Okay, like it's like a minimum threshold beyond which only like the precipitation formation would start. Okay, so this is like a line which should exist for any system that we are looking at. Like probably if you say aluminum, copper, magnesium, zinc, etc. Any system that we are looking at, this line should exist. Okay, only then we can say that the precipitate formation would be there. Okay. So if first and foremost, this line should exist. Secondly, we should go from the alpha range to the alpha plus beta range. Then only we can say that precipitate formation would start. Okay, because beta is the precipitate phase. Okay, alpha is your basically just the matrix, the initial matrix itself. So only when we cross over to alpha plus beta stage, we'll start seeing the formation of beta phase. Okay. So one important criteria for the solver's line is the solver's line should decrease with decrease in temperature. Now that puts certain restrictions on the solver's line, right? Or we can say in other words, that is the solid solubility should decrease as the temperature decreases. Right. So what does this mean? It means that as the temperature goes down, we can dissolve less and less of the other element, okay, the new element within the matrix. Okay, why that is true? Because as we know, right, like temperature, like all the solubility processes are temperature dependent. With decrease in temperature, obviously the solubility has to go down, right? So same thing is true here also. So here you can see that for the same like for the same weight percentage of B or beta, right? What would happen is if we are at this temperature here, let's say T1, we are seeing that it is soluble. A particular, like we'll see, like sorry, we are seeing that it is not soluble, so there will be formation of beta phase, precipitate phase, right? But as we increase the temperature, we'll see that at some other temperature T2, the solubility will increase. So now the beta phase is not formed because now the threshold for solubility has improved, and now we do not have this extra material which is beyond the threshold, right? So therefore there will be no beta phase, there will be only alpha. So it is also temperature dependent. That is something that you have to keep in mind. Okay. So this is how you can obtain precipitates. But what are the steps involved in forming these precipitates? Steps in precipitate formation. So first things first, you have to, okay, so let me first write down. No, actually first let me draw it. To be clear. So first you'll have heating the precipitate. So okay, this is temperature versus time. heating the precipitate to a large temperature, holding it there for some time, cooling it down, okay, then again heating it to a lower temperature, holding it there, and then finally cooling it down. This step-by-step process would result in the precipitate formation. Okay, make it a little bit more. So what are we doing? This is the way it is. First, we are heating the alloy to a very large temperature. Okay, so let me then write down the steps for that. Oh, actually, we'll see it first from the graph and then we'll write it. So first, we are heating it to a large temperature. Okay, and then what we are doing? We are holding it at that temperature for some time. Okay. Now, what does this holding do? It results in like this precipitates starting to like dissolve to an extent and like start forming some phases within the material system. Okay. So this temperature is so this part where you are seeing this holding, right? This is known as solution treatment. Okay. So you will see some temperature, let's say TL or something. That's where you're holding it. Okay. Then you will cool it down to some temperature, let's say T1. Okay. Again, you'll heat it to some temperature T2. Okay. Now, this individual steps, right? This will be done by quenching. And finally, holding it at the second temperature, the lower temperature, is known as leaching. Okay. So this is a step-by-step process by which precipitate formation will happen. Okay. So let's write it down one by one. What is happening at each step? Okay. So first step, solution treatment. First step, solution treatment. What you will do is you'll heat the alloy. Okay, it will begin by heating the alloy. Then you will result in the formation of single phase. Okay, what will happen is because you are heating the alloy, you have increased the temperature. So now you can add more of the secondary phase particle, the secondary element. You can add more of it. Okay, so you will see a single phase region. So this will dissolve any precipitate that might be present, any phase that might be present. Okay, so you will see a single phase region. So heating the alloy, holding it at a particular temperature, then you will see. Just a second. Single phase region, you will be seeing single phase region, and that will dissolve any precipitate or phase present. Okay, so anything that is present, it will get dissolved because the temperature is high. Now the solubility has increased, so anything can get dissolved. Okay. Now, once solution treatment is done, what you'll do is you'll do quenching. Okay. While quenching process, what you will do, you will cool very rapidly to room temperature or to lower temperature. Okay. Okay. So you cool very rapidly to room temperature or low temperature. Now what will happen is, because of this, now since the temperature is reduced, the solution which was able to dissolve more of the secondary particle or precipitate, etc., now will not be able to handle that much. The solubility will reduce, and therefore we will see a super saturated solution being formed. What do we mean by super saturated solution? Essentially a solution that has crossed the threshold of the saturation limit. Okay, the saturation limit is basically how much a material can be dissolved within the particular solvent or particular matrix. Okay, super saturated means it has crossed that saturation limit. It has crossed the saturation limit. Finally, you will again heat it to a little bit higher temperature, okay, and then hold it there for sufficient time so that precipitates can be formed. Okay, so this process is known as aging. So you're heating to a temperature, heating to a temperature, and then holding it there. Heating to a temperature and then holding it there, which will result in the formation of precipitates. Okay. Now this is why this process is known as age hardening, because of this aging step, right? So this aging step will ensure the formation of precipitate, which to which the dislocation interacts. Okay. So that is why this process is also known as age hardening. Okay. So essentially, what kind of microstructure would we see after every step? So let's say at TL, okay, which is the solution treatment part, we'll see microstructure just normally, okay, like there will be no change in microstructure, just like that we'll see microstructure, okay, being formed. Okay, you will see only one single phase, alpha phase. So after solution treatment, you will see something like this. Sorry, just give me a second. Sorry. Yeah, so coming back to the microstructure. So yeah, so this is at after solution treatment, you will get a microstructure something like this. Okay. Now when you are at T1, okay, so basically you have gone down, you have just quenched it. Okay, you will get a super saturated solution which will still not have precipitate. Okay, you will still have a similar kind of setup only. You still have alpha phase. You have exactly same as what we had before. Okay, after quenching, but this solution will be super saturated. Well, they don't have any precipitate, but the solution will be super saturated. Now, when you heat it to T2, basically you're doing aging, and you just keep it at that temperature. Now you will see the formation of precipitate. Essentially, this is your matrix, same as before. So there will be some difference in my drawing from matrix 1 to the other, but it's the exact same matrix. You can just assume it to be same matrix. And then you will see lot of this dots getting formed. Now these are the precipitates. Okay. So this is my alpha, and this small dots are my beta. Okay, which are the precipitates. So this is after aging. Okay. Now this aging process can be done by two different ways. We can either age it, we can either increase the temperature and then allow it to age at that particular temperature, or we can just leave it at that temperature after quenching. Whatever temperature we have after quenching, we can just leave it there. Okay, so based on what kind of aging treatment we are doing, we can call it either natural aging, or we can call it artificial aging. Okay, so in natural aging, essentially we have no external heat. After quenching, we just leave it at that temperature. And it will be very slow. So very slow process. But in artificial aging, we see there will be external heat. Okay, we are giving some external heat which will ensure that the aging process is fast. First, okay. So now let's talk about what are the characteristics of precipitation. Okay, what are the different characteristics with with aging? During aging, what are the characteristics that we will see for these precipitates? Okay, so precipitation characteristics. Okay, so essentially during aging, the characteristics of precipitates will change with time. Okay, with aging time, the characteristics will change. during aging. The characteristics of precipitates change with time. So, what are the different characteristics that will change? First thing first, the size of the precipitate would increase. Okay. Okay. Secondly, the distance between the precipitate will change. Changes. Third is the interface between precipitate and the matrix will also change. Okay. So whatever the interface is, basically precipitate matrix, whatever is the interface between them, that will also start getting changed as the aging process continues. Okay. So what are the steps or sequence by which this precipitation will happen during aging? So essentially, first you will have alpha phase, which is the supersaturated solution. Okay. Yes. Write it a little bit up. Okay. Now that will transform into something known as GP zones. Now these are like particles which are present within the matrix that do not act like precipitate, but do like create some sort of weird interface between the matrix and the whatever phase that GP is holding. Okay, so these are known as GP zones. They are like an interface in between the precipitate and the supersaturated solution, which will result after which will result in the formation of like first type of precipitate, which will be like theta double prime, then theta prime, and then theta. Now this step is very specific for like ALCU. Okay, so this what we are seeing is specific to ALCU, but Like a similar steps can also be seen for other precipitates. Sometimes you will not have all three theta prime, theta double prime, theta prime, and theta stages. Sometimes theta might not be the final state. Like that might not be the equilibrium precipitate. Sometimes in between precipitates might also be in equilibrium. Like theta prime might also be in equilibrium along with theta. So there are different sequences, but like in ALCU, alloy systems, we will normally see this to be followed. Okay. And this is like generally seen. So that is what we will take like as our learning process. For our learning process, we will take this type of presentation. Okay. So now that we talked about the interfaces between precipitate and matrix that changes during aging, what are the various interfaces that can be formed between these precipitates and matrices? Okay. So let's talk about interfaces. So first thing first, how would the interface look like? Like what essentially are we talking about when we are talking about interface? You want to see if the interfaces between the precipitate and matrix are kind of like coherent or they are incoherent. Like essentially you want to know whether they are actually fitting together very perfectly or they are having some sort of incoherency between their interactions. Okay. So the first type, of course, which goes without saying, is coherent interfaces. Perfectly coherent, essentially. So you have this kind of matrix, okay, and then you will have exactly aligned precipitate. Okay, so this is matrix, this is precipitate. We just write PPT precipitate, okay, and this is the interface. So this is perfectly coherent. Okay. Now what is the point about perfectly coherent? That one-to-one corresponding between precipitate and matrix, right? What we are seeing is one-to-one correspondence. Right? And because there's exact one-to-one correspondence, then there'll be no strain in the system. Secondly, there is coherent interface with strain. So I'll just write the title here this time. Just a second. Okay. Now here again you will have one-to-one correspondence between precipitate and matrix, but there will be some strain, which means that there is some misalignment. Okay, so how it will look like is something like this. You have this kind of matrix. The precipitate would be little bit misaligned in some places. So some small misalignment. Okay. So small misalignment between the matrix and the precipitate. Okay. So you still have one-to-one correspondence between precipitate and matrix. Then there will be strain. Okay. The third one is like as we are going forward, now the coherency will kind of break down. So you will have some semi-coherent interface. Okay. So what will happen in semi-coherent interfaces? Some level of coherencies will be there, but not completely coherent. Okay. So here we will see partial one-to-one correspondence between the matrix and the precipitate. Okay, so it will look something like this. So because there's some mismatch in between, there will be like some dislocations which will be formed in between to take care of this mismatch. Okay. We will essentially have this is my matrix. This is my precipitate, and these red lines are dislocations. Okay. So there is partial one-to-one correspondence between matrix and precipitate, and to take up the strain, we'll see the formation of dislocations within this interface. Okay. Partial one-to-one correspondence between matrix and precipitate. And dislocation will be formed to take up the strain. Okay. So here strain gets accommodated by the presence of dislocation. Okay. And finally, the last type of interface, as many of you might have already guessed, if now we have seen perfectly coherent, semi-coherent interfaces, the final one would be completely incoherent, so incoherent interfaces. So here it will just look something like this. Okay, and then you'll have precipitates which are like completely misaligned. Okay, so they are not at all coherent. So it is no one-to-one correspondence between the matrix and precipitate. Okay, so these are the different types of interfaces that can be formed. Now, how can these dislocations, now that we have understood about precipitate, water precipitate, etc., now let's see how dislocations can exactly interact with these precipitates. Okay, so now we're coming back to how the strengthening actually works. So let's write down interactions of dislocations. Now dislocation, sorry, yeah. So dislocations can cut or shear the precipitate. That could be one way they can interact, or there could be bowing. Okay. So essentially, dislocation can pass through by cutting the precipitate, or it can go around the precipitate and just bypass the precipitate. Or they can go around the dislocation, bypass. Okay. So let's study this one by one. So first, let's come to shearing. Okay, the first step, cutting or shearing the precipitate. Okay. So essentially, if you have precipitated something like this, and you have a dislocation, let me use a different ink. Let's say I have a dislocation here. Okay, moving in this direction with Burger's vector in this direction. This is my dislocation line. This is my dislocation. This is my precipitate. So after some time, what will happen is the precipitate will get sheared, something like this. Okay. So it will be displaced by some Burger's vector. And this is essentially after shearing. And the dislocation would move out with some similar dislocation line, will just move out. Okay. So this is how the shearing process will happen. Okay. Now there are certain factors that affect this shearing process. Let's see what are those factors. Okay, the shearing, factors affecting the shearing, or how easy or hard it is to cut the dislocation. Okay, first and foremost is coherency. It is related to coherency. So we talked about how there is some sort of interface, right? Coherent or incoherent interface. So this coherency associated with that, essentially the strain associated with this coherency interface, the coherent interface, that affects whether the cutting will be or shearing will be easy or not. Okay. Secondly, stacking fault energy. Again, very important. If there is a presence of stacking fault, because if you have certain particular types of dislocation, you will have stacking fault. So whether those stacking faults are present or not will also influence how the cutting would be. Okay. Third is if the structure is ordered or not. Very important, because if the structure is not ordered, then the dislocation motion would be affected by it, and then the shearing process also will be affected by to an extent. Next is modulus effect, of course, because how easy or difficult it is, it depends on the what is the modulus or strength of that particular precipitate, right? So the strength can be measured using modulus, so modulus effect would be there. The modulus effect of the precipitate. We are talking about modulus of the precipitate, okay? Next is interfacial energy. So what kind of interface is there will also influence what kind of interfacial energy we are seeing. That will indirectly affect the precipitate, okay? And then lattice friction stress. Okay, how easy or difficult it is to move within the lattice. So that friction that we are seeing within the lattice, the stress associated with that, that will also influence whether the precipitate will be like whether the precipitate will be like it will be easy for us to cut the precipitate or not. Okay. So one important relation that you have to remember from the shearing, there's only one relation that you have to remember. Just remember this, that tau should be the shearing stress is always proportional to root of r. Okay, this relation is something that you can remember. Okay. So since it is proportional to root of r, what we can say is the cutting will happen only if you have lesser amount of stress, right? You need less amount of stress to do the cutting. Then only the cutting will happen, right? So it will happen only when r is small or precipitate is small and coherent. Okay. The dislocation will prefer to cut or shear if the precipitate size is small and then it's coherent. If the precipitate is small and the interface is coherent. Okay. So this is the condition for preference for whether it will shear or not. Okay. This is the condition for that. Now the second way of dislocation interacting with precipitate is by bypassing the precipitate, okay, or bowing of dislocation. So let's talk about that. The precipitate. Little bit down. So how would this occur? Essentially, what is the bowing process that we are talking about? So how this occurs is essentially if we have dislocation just like last time. Okay, and then we have general precipitates being present. Okay, so some dislocation. Moving in this direction. Okay, this vector is also this direction. Now it interacts with the precipitate. Okay, so initially starts interacting. What I'll see is something like this. What we are going to see is something like this. Okay. So if this was my dislocation line, it was going from down to up. Still the dislocation line would be like that only. Okay. Now as the dislocation keeps going, it will keep going around the precipitate. Okay, it is not able to shear the precipitate. It has to keep going. So next step, what will happen is I will draw the last one. Yeah. So in the next step, what will happen is, now this bow, the two ends of the bow will reach very close to each other. Okay. So essentially, you will see something like this. Okay, they're very close to each other. Okay. So you'll see that this part of the dislocation has, if you see this region, right, you'll see that they are of opposite signs, the dislocation of opposite signs, right? And same thing would be here also. They are of opposite signs. So what will happen is, because they are of opposite signs, they will annihilate each other and they'll just interact with each other. Okay, they'll annihilate each other. So they'll just mix. Okay, and then we'll see that there is one, they leave behind some thing around the dislocation, and then the dislocation comes out separately. Okay, the same Burgess vector. It leaves behind a loop around the precipitate and just comes out. Okay. Um, so essentially, what is happening is, first dislocation interacts with precipitate and it starts going between the precipitate. Okay. So this step, second step, dislocation goes between precipitate. Okay. Next segment of the dislocation with opposite line vector will cancel each other. Okay. This step. Okay. And finally, you will see dislocation loops. So, how do we relate this dislocation, the shear stress associated with this dislocation? So, there's a relation between that. I just write down the relation. We'll not go in detail about it, but just 2 alpha GB by lambda. This is the relation. Okay. So, lambda is essentially the distance between the two precipitates. Okay. So, lambda you can say is proportional to kind of like r. So I can say like tau is proportional to 1 by r. This is a corollary that you can take from this. Okay. This relation you can remember for bowing of dislocation. Okay. So now if we look at shearing and bowing, how do we draw the curve? Where like where in which case will we see shearing happening or cutting happening? In which case we will see bowing happening? So if you draw the curves for this shear stress versus the radius r, using the two equations that we saw, tau versus r, if you draw, for cutting it will look something like this. cutting, it looks something like this. Okay. For bowing, it will look something like this. Okay. So this is how the bowing curve would look. You can make it little more. Okay. This is how the bowing curve would look. So finally, my net curve would look something like this. Okay. So let me just write. This is cutting or shearing. This is bowing. And this is my net curve. So there is a critical radius at which, like the highest value here. This is critical radius. At which bowing and shearing are both comparable. Okay, so both the mechanism would be active. So beyond that, you will see bowing. Before that, you will see shearing or cutting. Okay. So essentially, what you can say is, if the precipitate size is large, you will see bowing. Basically, if R is large, you will see bowing. If R is small, you will see shearing. And at critical radius, you will see the shift from bowing to from shearing to bowing. Okay. That is what is happening. Okay. Now let me just write it down. These two final points. Going around a dislocation will be preferred when precipitate size is large. Okay. And secondly, at critical radius, the bowing is comparable to shearing. Okay. And both the mechanisms will be active. Okay. Now, can we rewrite this entire discussion in terms of aging? Like what is happening during aging? So there is another curve known as aging curve. If we are looking at aging curve, we will see a similar pattern that we are seeing for this tau versus R. Okay, we'll see a similar pattern there also. So let's see what is aging curve. Now in aging curve, what is happening is, just a second. Yeah. Sorry. Just checking. Okay. So yeah, coming back to the aging curve. So there is one more type of curve known as aging curve, where you can have hardness. You can plot hardness versus the aging time. Okay. Let me just write it. Okay. Now, how this looks is similar to how the previous curve, tau versus R, looked. Okay. So you'll see similar kind of geography here also. So essentially, what will happen is initially starting from alpha supersaturated phase. Okay. It will move on to GP zone. So you'll have all these regions where GP zone is present. Followed by theta double prime, which will be somewhere here. Okay. Then you will reach the maximum, after which you will have theta prime and finally theta. Okay. Actually, theta will be last. You can say something like this. This will be theta. This will be theta prime. Okay. So there are like regions where you will see like GP zones, theta double prime, theta prime, and then finally you'll get theta. Okay. So this part of the curve, here's a different ink. Here you will see underage. Underaged part of the curve. Okay. Now this is overaged. And here where it is high, having the highest value of hardness, that is peak aged. Okay. Now just like last time, you will see that here you will see shearing, and here this region you will see bowing. Okay. So this is your aging curve. So you can relate this to tau versus R curve, and you can see that aging time and hardness also follows the same trajectory that you are seeing for tau versus R. Bowing and shearing you will see all around the same region only. So essentially, one more important thing that we have to keep in mind is effect of temperature on aging curve. Okay, how does temperature affect aging curve? So as the temperature decreases, increases, the hardness would decrease, as well as the time taken for aging will also decrease. Okay. Now, why is this happening? Because with increase in temperature, you see that the volume fraction of the precipitate would reduce. Volume fraction of precipitate goes down. Okay. Now, since volume fraction goes down, hardness will also go down, and also the time taken to reach peak hardness will also go down. So therefore, you will see this kind of relationship between temperature and aging curve. Okay. So this is another relationship that you can keep in mind. Okay. One last thing before we move to dispersion. So why exactly do we need to quench? Okay, why can't we do slow cooling after we have heated it to a high temperature? Why do we need to quench to form precipitates? Why do we need to quench the alloy after solution treatment and not slowly cool it? Essentially, what happens is, if we allow it to slowly cool, right? So supposedly this is my entire matrix, okay, and I'm allowing it to slowly cool. So what will happen is the precipitate would tend to form at regions where it is easy for the precipitate to form, right? So what they will do is most of the precipitate will start forming around the grain boundary, in the grain boundary region. They'll start concentrating around the grain boundary. Okay. Now this is bad because so this is the consequence of slow cooling. Okay. Now this is bad because now most of the precipitates are concentrated in the grain boundary region, and this will weaken the alloy as a whole. Okay. So this weakens the alloy. However, if we allow the precipitate to cool at a regular temperature, okay, if we allow it to quench itself, like if we instead of cooling it at a regular temperature, we let it quench, like we quench it, okay, we immediately quench it. So you will see that precipitate will be formed everywhere. Now this will strengthen the alloy. So you will see some precipitates being formed on the grain boundary also. So you will see some precipitates here also. Okay, but because you are cooling it, like you're cooling it very quickly, very rapidly, you're quenching it, you will see an even distribution of precipitate, which strengthens the alloy. So you can think of it like if the precipitate is getting formed at the grain boundary, what is happening is now dislocations which were interacting with grain boundary and were interacting with precipitate, both are now directly interacting together. So instead of strengthening, it is now weakening the whole thing. But now if precipitate and grain boundary are separate, they can interact freely, and then you will see a more strengthening like atmosphere within the whole alloy system. Okay. So this is about precipitate strengthening. Now let's move on to the last part, dispersion strengthening. So there's another strengthening mechanism. We'll not go in detail about dispersion strengthening. We'll just cover few things to understand how this dispersion strengthening works, because it's not that common, because precipitate strengthening is way more common than dispersion strengthening. But to an extent you can relate precipitate strengthening and dispersion strengthening. Okay. So here the strength is enhanced by addition of dispersoids. Okay. Let's move this a little bit up. Yeah. Now this again, like last time, restricts the dislocation motion. Okay. In every case, it's the same thing. It will restrict dislocation motion. Just I'm writing it so that you remember it. Restricts dislocation motion again. Okay. Now, what are the dispersoids? They are hard and insoluble second phase, which are not part of the matrix. Okay. Okay. So, how do we differentiate between precipitate and dispersion strengthening them? So, in precipitate strengthening, the precipitates are formed within the microstructure. Okay, so they are in situ. They are formed within the microstructure, in situ, or formed from the matrix. Okay, they formed from the matrix within the microstructure. And while on the other hand, dispersoids are externally added. Okay. Now precipitates also dissolves at higher temperature. Because it's part of the matrix and it starts dissolving when you exceed the temperature above and beyond a particular point, right? While dispersoids they are not like precipitates. They are not a part of the matrix, right? They don't dissolve. But they don't. Okay. So essentially, dispersoids will also act like precipitates only, but just that dispersoids have a much more like better condition in like it has one more extra condition added on, which is that it does not dissolve at high temperature. So for high temperature applications, instead of using precipitate, you can use dispersoids. Okay, but mind you that dispersoids are like dispersion strengthening is actually much more difficult than precipitate strengthening, which is why people prefer precipitate strengthening because it is much easier for us to form precipitates than dispersoids. Okay. One final thing that you can remember is the mechanism. So we have talked about the different mechanisms in precipitate strengthening, right? Here there's only one type of mechanism. Because it is not dissolved and it is not part of the matrix, the interface between the matrix and the dispersoids is always incoherent. Okay. is incoherent. Okay. So essentially, what we'll see is bowing around of dislocations. Okay. Only bowing. Because only if you have coherent boundaries, then only shearing will happen. Essentially, if you do not have coherent boundaries, like we discussed earlier, then you will see only bowing around of dislocation. Okay. So this is all for the theory part. Let's move on to the problems. Okay. Many of which problems that we'll be discussing today are theory only, because this there is not much equations or something involved here. So we'll just try to solve these theory questions and understand how this works. Okay. So with increase in the size of the precipitate, the magnitude of strengthening, what will happen? If you remember, let me just move this little bit down. If you remember this curve, just now I have drawn it, right? With increase in size, first you will see an increase in the strengthening and then decrease. So this is this option. Next question. The precipitation sequence for Al 4% copper alloy. So we have already discussed this, right? First we'll see alpha supersaturated solid solution, followed by GP zones, then theta double prime, theta prime, and then theta. So this is the second option. Next question. Among the following phase diagrams, which of the following can exhibit precipitation strengthening? So there are some certain criteria for precipitation strengthening, right? What is the most important criteria? We need to have a solver's line which is continuously decreasing, right? So that is possible in this option and in this option only. So only these two cases are possible. The other cases are not. Okay. Next question. Which of the following can be strengthened by precipitation hardening? Pure aluminium, no, because it's just a single metal. It cannot be. There cannot be formation of precipitate there. Similarly, pure magnesium also. Polymers, no. Polymers do not result in the formation of precipitates. And finally, aluminum copper alloy. That definitely we can see some sort of precipitation hardening there. Next question. Under tensile loading, a 2xxx series aluminum alloy failed in an intergranular manner after heat treatment. One of the most suitable reasons include the series aluminum alloy is intrinsically brittle. That is wrong. If it is brittle, then why should it fail in intergranular manner? Second option, alloy was solutionized followed by quenching, which resulted in supersaturated solution. Then there should not be any failure, right? Intergranular failure should not occur. Next option, alloy was solutionized followed by slow cooling, which resulted in formation of precipitates at the grain boundary. This is correct. If you do slow cooling, you will see formation of precipitates at the grain boundary, which will lead to intergranular failure. And finally, alloy was age hardened, which resulted in formation of coherent precipitates. That is wrong. Moving on. The figure below shows shear stress versus shear strain curves for same age hardenable alloy under two different aging conditions, A and B. Okay. Which of the following statements are correct? The first thing is A corresponds to peak age condition, whereas B corresponds to overage condition. Is it correct or not? That seems to be correct, right? Because if you think about it, the curve, this is my peak age, right? And here we have overaged, right? So A corresponds to peak age and B corresponds to overage. That seems to be correct. You will have higher tau value, shear stress value for A. A corresponds to overage, whereas B corresponds to peak edge is wrong. In A, dislocation predominantly interact with coherent precipitates. That should be correct because if it's peak edged, it has to be coherent. And finally, in B, dislocation predominantly interact with incoherent precipitate. That also could be a correct option. Okay. Okay. So next question. The most fundamental principle behind all conventional strengthening mechanisms in metal alloys is restricting the movement of dislocation. Of course, if you restrict the movement of dislocation, then strengthening will happen. Making them dislocation free, no strengthening can be achieved then. Making an easy pathway for dislocation, again there is no strengthening because dislocation are free to move. And heat treatment, no, that does not help. Okay, now moving on, this is a problem. Consider copper beryllium alloy with 4 atomic percent of beryllium. The initial precipitate size is 10 nanometer. If during the aging treatment the strength of the alloy increases from 200 to 550 MPa, what would be the change in size in nanometer of the precipitate? So we assume the precipitate to be coherent. So there is a relation that we have seen, right? What is the relation for coherent? So if precipitate is coherent, then we will see shearing, right? Shearing will happen. So for shearing case, there is a relation that we have written down. Tau is proportional to root of r, right? This is the relation. So I can write tau 2 by tau 1 is equal to root of r2 by r1. Okay. Now here r1 is given to be 10 nanometer, tau 1 is 200 MPa, tau 2 is 550 MPa. So if I rewrite, it will be 550 by 200 will be equal to root of r2 by 10 nanometer. So I'll get r2 to be equal to, let me just calculate. One second. So I am getting final answer to be 75.625 nanometer. That is R2. They are asking what would be the change in size. So change in size would be R2 minus R1. Just move this little bit down. Change in size would be R2 minus R1. So 75.625 minus 10. So that would be 65.625 nanometer. So this is the answer. Okay. Let's see how we have solved the problem. Next question. A pure metal can be strengthened by a pure metal can be strengthened by dispersion strengthening, precipitation strengthening, again no. So dispersion strengthening, precipitation strengthening again cannot be given for pure metal, it is only for alloy systems. You need to have more than one alloy system. Okay. Strain hardening, interacting with other dislocation, that is possible. Solid solution strengthening again not possible, you need to have another metal system to have solid solution strengthening. Then which are true for precipitation or dispersion strengthening? The precipitates are stable at high temperature but dispersoids are not. That is wrong. Dispersoids are stable at high temperature but precipitates are not. That is correct. Interface between dispersoids is incoherent. That is correct. In precipitate strengthening, the stress required to cut the precipitate increases as the size of the precipitate increases. That is true. Right? Because it is tau is directly proportional to root of R. So as the root R increases, the stress required to cut the precipitate would also increase. Okay. So next question, let me just move it. Okay. This is question number 11. Consider a precipitate strengthened aluminum alloy. Okay. Precipitation strengthened aluminum alloy. After an appropriate heat treatment, the microstructure of the alloy consists of precipitates with mean spacing of 0.2 micrometer. Compute the shear stress required for Oro1 bowing of dislocations of this material. Okay. So they have given you lattice parameter, they have given you shear modulus, they have given you also alpha value. Okay. So aluminium is FCC, right? So for FCC, we have Berger's vector to be A by 2, 110, right? So mod of B, the B that we need for the equation will be equal to A by 2 root of 1 square plus 1 square plus 1 plus 0 square. So that will be A by root 2. Okay. Now A is given to be 0.2 micro, sorry, A is given, A naught is given 0.4 nanometer. So 0.4 into 10 power minus 9 divided by root 2 nanometer. That's my B. Okay. So if I calculate this, B will be equal to, let's calculate. So this is 0.2828 into 10 power minus 9. Nanometer. Okay, that's B. So now they have asked us the shear stress required for Oro-1 Boeing, right? So we have already seen the equation before, 2 alpha GB by lambda. So all the quantities we have, alpha is given to be 0.5, 2 into 0.5 into G is given 30 GPa, so 30 into 10 power 9 into B is given 0.2828 to 10 power 9 into 10 power. Okay, let me just divide by lambda. Lambda is given as 0.2 micrometer, so 0.2 into 10 power minus 6. Now let's solve this. Get a final answer. So the answer is 42.42 into 10 power 6 Pascal. Or 42.42 megapascal. Okay, this is the final answer. I hope you have understood how we have solved this problem, and also like how we have I hope you have all understood the concepts that we have discussed today, including the different types of questions that we have come across. In any case, if there are any doubts, any questions that might arise later, you can just ask me, okay, in the subsequent sessions. So with that, we will come to an end for today's session. I thank everyone for listening in. We'll meet again next week. Thank you.